so he came a short little distance to visit with us today. Maybe that's such a short distance. He's been with VG Scienta for a few years already. Before then, he was working with Vattenfall, which is one of the major energy-producing companies in Europe and one of the largest in Sweden. And before that, he got his doctorate in physics at Uppsala University in Sweden. And he'll be talking to us about what's new in the world of X-ray photoelectron spectroscopy.
All right, thanks a lot. Let's see if we can get my presentation out.
Great.
Very good. I think you have to go to the first slide. Oh yeah, great, excellent. All right, Henrik, first of all, thank you for inviting me, and I'm very happy to be here today to discuss or try to lay out the elements of photoelectron spectroscopy and XPS, and ambient pressure XPS in particular. And I'm glad that there's so many people here. Yeah. I don't think I need to introduce myself. I work for VG Scienta, as was mentioned, and VG Scienta is basically a company which contains two business divisions. In the United Kingdom, we have a factory that produces essentially vacuum components. This is the continuation of the original vacuum generators going back to the 60s. It was one of the first companies actually doing UHV equipment. And there's another part where I work currently at Uppsala, Sweden, where we make scientific instruments primarily related to photoelectron spectroscopy. And together we form a global company. We have factories in the UK and in Sweden. We have sales offices in all major markets. We have a sales manager in Denver, Colorado, here in the US, who unfortunately couldn't be with us today. So that's the basics of the company. And the scientific instrument division that I belong to was founded by Professor Kai Sigban in the early 80s, essentially immediately following his Nobel Prize in physics in 1981, and he was awarded the prize for his instrument development within the XPS. So the company was founded to commercialize his development. So we are building onto a tradition that goes back to the 1950s. So I dare to say that we have quite some experience in this field. We made a name for ourselves in the early 90s where we developed the 2D detection capabilities, especially geared towards simultaneous measurements of kinetic energy and emission angle. And I'll show you an example of why that is so great later. And today we are supplying photoelectron spectrometers and related equipment to researchers all over the world, especially in the fields of angular result photoelectron spectroscopy and ambient pressure photoelectron spectroscopy that I will go into some details about later. And we have a small but enthusiastic R&D department in Uppsala, and I'll show you some of our latest releases. So photoelectron spectroscopy is all about measuring the energy levels of a material. And these energy levels, as I'm sure you're aware, are quantized. They can be considered as being either core levels or valence levels. And the primary difference is that core levels have a much higher binding energy. They are close to the nucleus, and they remain essentially localized and atomic-like even in bulk material, whereas the valence levels delocalize and form electronic bands. And photoelectron spectroscopy is essentially the process of, by using a well-defined photon, ionizing one of these electrons and measure the kinetic energy of the outgoing photoelectron. And this is using the photoelectric effect that, of course, gave Albert Einstein his Nobel Prize in 1921. And the binding energy, which is the thought information in this kind of technique, is found as the difference between the photon energy and the kinetic energy. And of course, in order to accurately determine the binding energy, you need to accurately determine the photon energy and the kinetic energy of the photoelectron. So these are the sort of top-level instrument challenges involved in XPS. Photoelectron spectroscopy can be applied either to core levels or to valence levels. And of course, in both cases, the same mathematics apply. Now, here comes a little bit of terminology. Core level spectroscopy can be divided into a number of subgroups, where X-ray photoelectron spectroscopy is sort of the basic technique that is used in labs all over the world. This is a pretty common technique. And I'll show you the basics later. Ambient pressure photoelectron spectroscopy is essentially XPS done at anything higher than UHV pressures. And there are some technical challenges involved in that gives it a certain feeling. You need to do certain instrument adaptation in order to do that. Hard X-ray photoelectron spectroscopy is essentially XPS using high photon energies, several kilo electron volts. And that can be used either to probe very deep core levels, to get access to information that is not available with more low photon energies. But more often it's used to give with a high photon energy, you can give a high kinetic energy to the outgoing photoelectron. This means that you can penetrate from deeper within the material, and you go from a relatively surface sensitive technique to a more bulk sensitive technique. Valence level spectroscopy is essentially divided into a few different subcategories. Ultraviolet photoelectron spectroscopy is maybe the basic version where you study the density of states as a function of binding energy. Now, for band structure, there is also momentum information in this band, and there's one way of actually measuring that directly is to use the angle, the emission angle of photoelectron, because they contain information on electron momenta. And in that specific version of the spectroscopy, this is called angle resolved photoelectron spectroscopy. And finally, you can do this not only angle but also spin resolved, and then you get sort of another quantum number determined. So these are the flavors of ultraviolet or valence band spectroscopy. Today I will focus on this side of the scheme. Before we go to that, I'd like to introduce how we generally measure the kinetic energies of the photoelectrons. And in most cases, this is done with a hemispherical analyzer. And this analyzer contains two concentric spheres. And by putting them on opposite voltage, you can have your electrons go through the lens and into the hemisphere, and it will bend to different degree depending on the kinetic energy of the electrons. To the left, you see sort of the hemisphere from the side, and you can see here that electrons that enter at the same position, electrons that have a higher energy, they will bend less, and they will end up at this side of the detector, which is placed in this position. Whereas electrons with a lower energy, they will bend more, and they will end up on this side of the detector. So with this setup, it's possible to measure different kinetic energies in parallel. But not only that, with the use of a 2D detector, we can also probe another property perpendicular to the energy dispersive direction, so that will be out of the paper. And we use this to do either angle resolved measurement or position resolved, spatial or imaging measurements. To the right, you see sort of a schematic example of an angle resolved mode. And in this way, the analyzer is set up in a way that electrons that are emitted with different emission angles, even originating from the same position, will end up at different positions at the entrance of the hemisphere. And when they do that, they will end up at different positions of the detector. And that means that we get the possibility to record these kind of snapshots where you have kinetic energy along one axis and you have emission angle along the other. This is the surface valence band state of gold, and you can see the band dispersion. And the intensity is actually a function of both kinetic energy and emission angle or momentum. So the angle mode is a powerful technique because it enables parallel measurement of both emission angle and binding energy. And this can be done in a number of different ways, or can be used in different ways. And probably the most common is to use this for band mapping or band structure measurements, where you're looking at the valence levels and measure the electronic properties as a function of energy and momentum. But this can also be used for parallel and non-destructive depth profiling, as I will show you later. And it can also be done for more exotic things like X-ray photoelectron diffraction, which I will not go into today. And the angular result spectroscopy essentially was invented by Björn Wannberg at Scienta. He's a long time with the company, and has been with us since the founding of the company in the 80s, and still very active, although he's slowly phasing out, he's pushing 70. So we go to the application areas, and I said I will focus on the ambient pressure photoelectron spectroscopy. But before we get to that, I'd like to say or introduce the XPS technique, because essentially the type of information that you extract in ambient pressure XPS is very similar to, let's call it, standard XPS. And the beauty of X-ray photoelectron spectroscopy is that the measured binding energies contain both element and chemical state specific information. To the left you see an example of elemental characteristics, and this is a silver sample. And you see the electronic levels appearing as sharp peaks. In this spectrum you see also a little bit of carbon contamination, which means that XPS is an excellent technique to do elemental quantification. There's a little bit of math involved, because you have to know the ionization cross-section for each of the elements as a function of photon energy. But doing this, there are very well established routines that help you actually distinguishing or finding out the elemental composition of your sample. But even within one of these levels, to the right you see an example of 4 peaks, which are all C1s peaks. Even within one electronic level, there are subtle differences in binding energy due to the fact that different carbon atoms are exposed to different chemical surrounding, and that affects the binding energy. This is a molecule which has 4 different carbons, and they all have different chemical surrounding, and this surrounding affects the binding energy to the extent that you can actually see them as separate peaks. And this is the reason why XPS is sometimes called SGAL, which is an acronym for electron spectroscopy for chemical analysis, because you are sensitive to the chemical surrounding of each atom in the material. This is a molecule that was designed by Professor Kai Siegmann to show this. He was looking for a molecule that had 4 nicely separated peaks. It's not always that simple. Sometimes peaks are much closer, and sometimes they are even directly overlapping. So if we go to the ambient pressure photoelectron spectroscopy, this is a special field, as I indicated already, because traditionally all photoelectron spectroscopy requires UHV. Now, unfortunately, not all systems and processes can easily be studied at UHV. And this may be either because the samples are not compatible with UHV. They can be volatile, or they can be even liquids, or they can be biological, and they don't like you to expose them to vacuum. But probably more important, some processes are fundamentally different at elevated pressures compared to UHV, and this is the case, for instance, in catalysis. Which means there are a lot of studies that benefit from doing this at elevated pressures. Now, there are 2 problems with trying to do this, essentially. First problem is that some components of the instrumentation are sensitive to higher pressures. The detector is a special case because it requires some level of vacuum. But also in an electrostatic analyzer, there are high voltages involved, and if you're not careful, you may have discharge problem. But more importantly even is that the photoelectrons coming off a sample that is surrounded or immersed in a gas atmosphere, they tend to scatter on the surrounding gas, and this scattering can be pretty substantial, and they prohibit the photoelectrons from reaching the detector. Now, the good thing is that both of these problems can be solved by invoking a differential pumping scheme to the instrumentation. Ambient pressure XPS, or ambient pressure photoelectron spectroscopy, contains a very large pressure range. Now, unfortunately, we are not yet in a position to go all the way up to atmospheric pressures. The current state of the art is somewhere about 25 millibars of pressure, which is also a reasonable range because it contains the vapor pressure of water at room temperature, which is a very important pressure. It allows a lot of important studies. But essentially everything that is above UHV is called ambient pressure XPS, and there's a big range. And although a lot of work is targeted to at this levels essentially because water is such an important solvent, there are very interesting work being done in this whole range. And depending on your scientific interest, you may be across the whole range or focusing on a narrow level. Typically, heterogeneous catalysis is done for a very large range, whereas water chemistry naturally focuses on the vapor pressure of water and so on. There are some certain special cases like ionic liquids that virtually doesn't have a vapor pressure, which is essentially done at UHV, although they are liquids. So this is a broad field, and depending on what you want to do, you may end up in very different pressure regimes. At Scienta, we have developed several analyzers devoted to ambient pressure spectroscopy, and I show two of them here, a smaller R3000 based analyzer to the left, and our most recent R4000 HIP3 analyzer to the right. In both of these cases, and in all cases, these differ from traditional electron spectrometers in that they have several differential pumping stages. They also have a very small aperture that separates the sample and the gas surrounding the sample normally from the electron spectrometer. This picture shows the differential pumping stages of the HIP3 analyzer. And you can see that the sample is placed just outside this first aperture. And you see that when the photoelectrons go through the analyzer, eventually ending up at the detector, it goes through several differential pumping stages that gradually lower the pressure in order to ensure safe operation of the detector over here, but also in order to reduce the electronic scattering. And it's important to, in this design, that the action has to happen very close to the top. You have to be able to reduce the pressure very rapidly upon entering the analyzer, because the inelastic mean-free pass of photoelectrons at 25 millibar of gas is extremely short. It's hundreds of microns. So in order for any photoelectrons to get through and into the analyzer and successfully arrive at the detector, you need to be able to decrease the pressure very rapidly, very close to the sample. And here's a pressure simulation of one of our analyzers. And essentially there are two things to this. And the first thing is that the sample needs to be placed very close to the aperture in order to decrease the distance that the photoelectrons need to travel in the gas atmosphere in order to reduce the scattering. But at the same time, you can't be too close, because if you get too close, you will start pumping on the sample and you will not have the pressure immediately above the sample that you think you have. So the current most common rule of thumb is to have the same distance between the sample and aperture as the aperture diameter, and this is typically hundreds of microns. So you're very, very close to the analyzer with the sample when you do these experiments. The second important part is that as soon as you enter the analyzer, the pressure needs to decrease very rapidly. And indeed, you see here that within one diameter away from the intersection, the pressure is already 10⁻⁻² millibar range. And this is very important in order to reduce the scattering and make sure that you get the maximum signal, because for electrons, inelastic scattering is really a hurdle to overcome when you try to do this kind of experiments. And there are a lot of design involved in order to ensure that the pressure is indeed decreasing as rapidly as possible. And we have installed somewhere around 10 different ambient pressure XPS installations all over the world. And these are both systems that we have delivered and systems where we have delivered the analyzer, and the end user have built the rest of the system. And these are also both synchron end stations and lab systems. And this is probably around half or a little bit more than half of the ambient pressure systems that is out there at all. So this is a fairly new field. The field was pioneered in the early 2000s, probably, and it's a rapidly growing field. Yep, for sure.
Henrik, can you comment about the R3000 versus your new model? So what are the capabilities? I mean, you have it there under the 10⁻⁻1 millibar or 1 millibar category. Can you comment about that?
So there are essentially two things that we go back to. There are two things that the R4000 based model can do that the R3000 cannot do. And first is that it goes to much higher pressures. So the R3000 model is limited to 1 millibar, whereas the R4000 is specified to 30 millibars, but we have run it to 50 in the factory. We know that at the Advanced Light Source in Berkeley, they were running it at above 100. So it can go to much higher pressure. And the reason is that the R3000 has the differential pumping sort of integrated into the normal size of the analyzer, whereas the R4000 has an extra separate pre-lens, and the pre-lens makes it longer and gives a much better pumping. So the pre-lens contains both differential pumping stations but also refocusing electrostatics in order to make sure that you get a much better pumping but still don't lose any signal.
You're probably going to talk about this in a few slides, but on the 4000, which I'm familiar with your literature, it has an in situ cell, like environmental cell. Is the 3000 also equipable with the cell?
No, we haven't done that
Okay.
for different reasons.
Okay.
But let's come back to that when we talk about the cell, the way that we realized ambient pressures. So I want to show you just a couple of examples of what kind of research you can do in the field of ambient pressure for electron spectroscopy. And I'm going to do that using two installations. One of them is at the University of Pennsylvania, a group of Rob Karpik, and they use an instrument based on R3000 analyzer. And the other one is from the Advanced Light Source in Berkeley, and this is a synchron end station, and it's using an R4000 based analyzer. And this is the first example from UPenn, and this is a case where the parallel angle resolved capabilities is used to perform parallel non-destructive depth profiling. And that's based on the notion that electrons that go out normal to a surface, they can originate from deeper within the material than electrons that go out grazing. And if you can measure several of these emission angles in parallel, which is exactly what we do with angular mode, then you can compare them, and by doing that you can obtain information on the depth structure of your material. In this case, this has been used to measure the thickness of the native oxide layer on top of silicon. And in that case, you measure several emission angles in parallel, and these are plotted in this layer. And sort of regular spectrum correspond to more grazing and emission. And when you do that, you can see that the ratio of bulk silicon to silicon oxide changes. And with that, you can actually calculate the thickness of the oxide layer. So this is a way of obtaining depth profile information. Now, traditionally, this has been done either by measuring and then spot away a little bit of material and measure again and spot away a little bit of material. Or alternatively, by measuring at normal emission and then measure several times with more and more grazing emission by rotating the sample. Now, the beauty of doing it in this way is that you obtain a snapshot picture. You get all of the angles at the same time, and especially for ambient pressure spectroscopy, this may be important because normally you have a chemical reaction ongoing here, and if you do it first normal and then grazing, you don't know if you're looking at the difference between the angles or if you're looking at differences because time has elapsed between the measurement. So this is really a powerful tool when it comes to ambient pressure photoelectron spectroscopy, because you get a snapshot picture and you know that the whole information is from the same time. The next example is a spatially resolved photoelectron spectroscopy. And this is a study from the Advanced Light Source. This is a study of a solid oxide electrochemical cell. These cells can be used as fuel cells. And in this case, sort of a special one-dimensional version of this device was constructed, and it was measured with XPS during operation. So in an atmosphere of oxygen and hydrogen of around 1 millibar, the XPS spectrum was taken in a way that we distinguish not only for different binding energies, but also different position along this device. And that's what you see here. So you have binding energy on this axis, and you have position along the device on this axis. And when you do that, you get access to the local electronic properties of the material at different positions of this device. And in this case, you're looking at a 0.4D core level, and you can see that in this region, you see a bending of the band, and the length of this sort of bended area tells you that the active area of this device is, in this case, 100 micrometers wide. So you can actually obtain very specific spatially resolved electric properties of this device. In this case, the spatial resolution is around 20 micrometers. These cases and a lot of more examples of studies can be found on our webpage, and I encourage you to have a look at it if you're interested in what can be done. Scienta.com, and click on the Publications tab. It takes you to a search form that you can put in your preferences and get a list of scientific papers. This is by far not a complete list of the papers that has been done with our equipment, but it does contain quite a few papers. So finally, I'd like to show you the outlines of our most recent product. And this is a lab system for ambient pressure XPS. It's based on the HIP3 analyzer. Now, the HIP3 analyzer is a newly developed ambient pressure photoelectron spectrometer for the combination of ambient pressure and imaging XPS. And it's based on our previous models, but whereas the HIP2 analyzer was developed for synchrotron radiation, it went all the way up to 10 kiloelectron volts. This one is really optimized for standard XPS energies, which means up to 1,500 eV, which makes it a perfect match with an aluminum K-alpha source. And it's got two interesting properties. One is that it's got something that we call the swift acceleration mode that increases the transmission dramatically, especially at ambient conditions. And it also got a pretty nice imaging mode with a resolution of less than 20 micrometers.
Henrik, how about the analyzer?
The energy resolution of the analyzer is the least concern. It's the guaranteed energy resolution is 15 millielectron volts, which is much better than what you can get from a lab X-ray source, which is around 200 millielectron volts.
Even when you go up to whatever pressure?
Yes, it's not affected by the pressure.
Okay.
The energy resolution do not deteriorate when you go to ambient pressure. So, in fact, the energy resolution of the analyzer is better than it needs to be, because for core levels, your experimental line would be dominated by lifetime broadening in most cases. The swift acceleration mode is a trick that we pull when we put a high potential, not on the first cone, because this is exposed to the gas and you will be interfering in the experiment, but on the second aperture. When you do that, you accelerate the electrons going into the analyzer. And that means that with the high kinetic energy that they obtain, the scattering cross-section drops dramatically, which means that the reduction in signal due to scattering in the surrounding gas is much less severe than it was for previous models of ambient pressure analyzers. And this gives an increase of transmission at high pressures of up to 10 times, which means 10 times faster measurements, which does make a big difference if you go from 10 hours measurement to 1 hour, or from 1 hour to 6 minutes. So this is actually very useful, especially for the highest pressure, because already there you see the limitations of the scattering. The imaging XPS is a parallel imaging mode where you have a field of view of around 0.8 millimeters, which matches the aperture size of the ambient pressure high pressure gas cell pretty well. And within that field of view, the spatial resolution is around 20 micrometers. And here are some first results. These are only a couple of weeks old, done in the factory. And we've done this test with a special sample. This is a silicon sample with thin gold lines. And we zoom into an area where the gold lines are 40 micron wide. And we can perform spectroscopy in this sort of box here. So we get spatial resolution along in one direction. And when we do the measurement, we get detector images that looks like this. We have kinetic energy in one direction, and you have position in the other direction. Now, this is a very broad line in energy, so you don't really see a lot of structure in that direction, but you can see that these lines correspond well to these lines. I'm not sure how well you see that. Very difficult. You have to use a little bit of imagination. You need to reconsider my colors. All right, now if you zoom into this and you look at the slope of these lines, we can confirm a resolution better than 20 micrometers, and we're targeting a resolution of 10 micrometers. And this is very much work in progress. This analyzer we aim to deliver in a complete lab system. And this is a pretty neat little thing. It's a combination of a fairly standard XPS system that also has provisions for ambient pressure capabilities. And so it's got an analyzer, there is a monochromatic X-ray source, and they're both looking at this mu metal analysis chamber. And inside this chamber, it's better shown in the next one. If you remove the chamber, there is a high pressure reaction cell mounted on a manipulator. And when you do ambient pressure experiments, you press this cell onto the analyzer. So the small aperture that I was describing briefly in this way, in this setup, it is integrated into the cell. And that means that it's only this small volume, which is about 50 cubic centimeters, that is exposed to the elevated pressure when you do your experiments. And the rest of the chamber and the rest of the system is under vacuum. And that means that when you do your usually a pretty dirty experiment. When you're done, you can pull this cell out. There's a gate valve, you close the gate valve, and you can remove the cell. You can do that by sliding the hole a little bit backwards, and you can clean it, or you can even take it out and put in a second one. And with this setup, you avoid the problem of cross-contamination, which is always a problem with ambient pressure XPS in the traditional way of doing it, which we are filling the whole chamber with gas.
Can you run multiple samples?
Yes, but only one sample in the gas cell at a time.
Okay,
At
just one
this
sample
time,
at a time.
yeah.
How long to, insert, do the measurement and pull out, assuming?
It's pretty fast. We haven't clocked it, but it's pretty fast. There's a load lock here, so you take the sample out, and you can change the sample here without having to open it all the way like this. There's a standard load lock here. So it's pretty fast, but I can't tell you in seconds.
Do you have pressure and temperature control on your cell as well?
Yes, and you can run this either in a static way where you keep the pressure, and you're always going to have a little bit of leak because you have an opening into the analyzer. You can have that as small as possible, so you just compensate for the gas that you lose into the analyzer, or you can run it in a flow-through mode where you have a gas inlet and a gas outlet. And the gas outlet is equipped with an RGA, so you can monitor if you're doing a catalytic experiment, you can monitor your reaction products in parallel to your XPS data. And, let's see. Okay, I better go. Oh. I redid this just before the presentation, never a good idea. Once you have the gas cell out of the analysis chamber, there is a secondary UHV manipulator that can come in and do all your standard UHV XPS work, which means that in addition to being an ambient pressure XPS station, this is also a sort of full UHV XPS system. And you can transfer samples between them if you need to. One of the limitations of the cell is that because the sample has to be so close to the aperture, there's only limited tilting capabilities within the cell. If you want to do more large scan ARPAS kind of measurements, you can do that in UHV, and then you take the sample out of the gas cell onto the UHV manipulator, and you get access to all of those capabilities. There's also higher heating and cooling range on the UHV manipulator compared to the gas cell. With that, I think I want to thank the people at UPenn at ALS for allowing me to show their data, and thank you for your attention.
Can you please comment and elaborate about the in-situ cell itself, its capabilities,
Yeah, all right, yes.
like what temperature ranges can you operate?
Yeah, this sample temperatures in this cell is down to liquid nitrogen temperatures and up to, depending on the options, up to 800 C or something in that range. And you can heat a sample in several ways. So you can have a resistive heated, but if you need the highest temperature and the best control, you can also heat it with a laser from the backside. And I'm not sure the temperature range in that case, but that's an available option. The sample pressures up to around 30 millibars, either in static or in flow mode. What else can yeah. Any more properties do you think I should elaborate that I can think of at the moment?
No, that's fine for now. We'll talk later.
Yeah, sure.
Just curious, can you bring a laser into the sample? If I want to look at laser effects on material.
Yes, you can. So this cell is not shown here, but it's got windows for X-ray to come in, and you can place additional windows around the cell. If you want to get in with lasers, or if you want to do simultaneous IR or Raman kind of studies or anything like that. There is the capability to come in. And this design is newly developed. We had a previous design that we've been discussing previously, and the new design has a much better flexibility in terms of the possibility to bring in additional techniques.
How many windows, additional windows?
How many do you want?
4.
Okay, I'm sure we can do it.
Okay.
No, this is still big. The fine details are still being worked out,
Okay.
and there's always possibility to customization. But 4 doesn't sound.
Okay. I'm just.
We'll see where we end up.
Hey, can you, again, it's important, I want to better understand the 3,000 versus this new
Yeah,
4,000 HIP 3.
yeah,
So when people are using the 3,000, they are basically just hanging their sample in a larger chamber,
yeah,
and it's just soaking and being bathed in the gas.
yeah.
And they do they have the RGA, residual gas analyzer in that system?
You can have that, yes.
Yeah, okay. But if the catalyst, or if you're doing a catalytic reaction, since you have this sea of reactant, you may not be able to detect much in this, because you're just hanging the sample. And the gas is static in those systems?
Generally, yes.
Yes, okay.
No, yeah, it is more of a brute force method.
Yes.
Especially for heterogeneous catalysis, the gas cell version is much neater.
Oh, yeah, that's the only way to do it, of course.
Yeah.
Meaningfully.
The other version, where you have a larger, more of a traditional analysis chamber, you fill the whole chamber with gas. It's got its advantages if you want to put in really bulky equipment. But if you do this kind of studies, this is way neater.
Thank you.
About the laser question, on your HIP 4000, you have a viewport at the end of your analyzer that is exactly going out of your cone. Does that have the same? Will you have the same thing here also? So you can shine the laser all the way from the back.
Yeah.
So okay.
But this is generally not used for heating. This is used for alignment.
Right. But I mean, if you can.
Yeah. We have that. Yes, and that's a very practical, but a very useful tool for sample alignment.
Let's thank the speaker again. Thank you. Just to frame the conversation a little bit, Lehigh University has had for over 25 years what was the top-of-the-line XPS equipment from Scienta. It's been a very, very busy and well-used tool. For the last several years, we've been looking into the possibility, considering the possibility of getting into environmental XPS because we have such strong interest in catalytical studies and other things like that. So what you're hearing about today is not, what you heard about today was not a tool that we have, but a tool that we're extremely interested in acquiring, hopefully in the relatively near future. So that just frames it. On the other hand, the technique that you're about to hear next